Tonight we step quietly into deep time, not to stir fear, but to ask an older-than-starlight question. How will our universe meet its end? Picture a clock made of galaxies, its single hand a hush of redshift, sweeping outward. Space is widening, distances learn a new patience. The arithmetic of the sky changes by degrees too small to feel and too faithful to ignore. We will read that arithmetic like tide tables for eternity. First, the gentle futures, heat slipping evenly across the cosmos until nothing is left to drive a wind. Then softly, we will press a fingertip to stranger doors, a universe that tears its seams, a cosmos that turns and falls back through its own past, a vacuum that might, in theory, choose a truer state and rewrite the rules inside it. Every term will wear a plain image you can rest in. Dark energy as a quiet pressure filling the room of space. Entropy as the evening of contrasts, like daylight thinning to one colour across a calm sea. Black holes as long keepers who, at last, exhale their stored light and go quiet. Nothing here asks you to hurry. The endings we consider are farther away than language knows how to count. They are ideas you can hold, examine, and set gently down before sleep. Before we begin, let us gather our little midnight crew. If these voyages bring you ease, a gentle like or a simple subscription helps this calm reach others still awake. Tell me the hour you are drifting tonight in the comments, whether that may be midnight, 2 a.m, or even dawn's edge, so I can chart our resting constellation and time future journeys to meet your night. And if you want to sink deeper, the Midnight Voyager playlist is waiting. Settle your shoulders, loosen your jaw, let the breath fall in and out, unforced. We are going to the far future now, step by step, light by light, until even light forgets to hurry. When you are ready, we begin a calm voyage through endings that are, at heart, only another kind of rest. Settle into a slow breath and imagine the sky as a patient ocean, its surface widening with every heartbeat you do not count. Space itself is stretching. The marks we make across it drift a little farther apart. This is the quiet background of our era, an expanding universe whose pace is gently increasing. The cause we call dark energy, a smooth pressure woven through the fabric of space, not rushing, only urging. Most evidence suggests it behaves simply, like a steady property of emptiness. If that remains true, the far future will be an unhurried cooling, a long evening rather than a storm. Entropy gives that evening its direction. It is the tendency of differences to fade, of steep hills of heat and light, to wear down into low plains. Stars exist because the universe began with sharp contrasts. They live by moving energy from hot interiors to cold space. Across vast spans, those contrasts soften. The cosmos, like a lake after a strong wind, becomes glassy again. Not all at once and not soon, but steadily. First comes the fate of stars. The massive blue ones burn quickly and go dark. Suns like ours take their time. The smallest red dwarfs endure for trillions of years, careful and dim. Star birth slows as raw gas is spent or heated and scattered. Then it stops. A galaxy in that age would look like a winter city at night, window after window darkening, until only a few pale rooms remain. Orbits continue. Worlds, if any still circle Embers, move through long seasons. The quiet is complete enough to hear the arithmetic of gravity. What remains are remnants. White dwarfs cool towards blackness. Neutron stars keep their dense silence. Planets freeze or fall inward. Over longer intervals than we have numbers for in ordinary speech, even the remnants change. Black dwarfs, stellar hearts gone cold, may become the most common stellar bodies, though none exist yet. Their heat will leak into the deepening night with a patience that defies metaphor. Then the black hole age arrives, not as a takeover, but as a narrowing. Black holes gather what can fall and wait out what cannot. Even they are not final. At their horizons, a quantum process allows them to radiate, slowly losing mass. The largest will take a time so immense it feels like a new kind of number, years stacked into towers beyond counting. They evaporate to brief, soft flashes, and the darkness they leave behind is thinner and more even than before. The sky is still there, but there is little left to light it. Alongside this long fade stand other possibilities. If dark energy's pressure were more negative than it seems, expansion would quicken into a future with sharp teeth. Galaxies would drift beyond each other's reach, then galaxies themselves would unthread. Later, stars and planets would be pried apart. In the final moments, even atoms would fail to hold. This scenario, called a big rip, requires the cosmic pressure to be stronger than current measurements suggest. It is not the favoured path, but it remains in the margins of the map, a reminder that the character of dark energy is measured, not decreed. There is also the old dream of reversal. If expansion were to slow and turn, everything would begin to fall back together. Temperatures would rise again, densities would increase, the universe would end where it began, or pass through that ending into another cycle. For that to happen, gravity must overtake whatever is pushing space apart, or dark energy must change its nature with time. Observations today make a turnaround unlikely, yet the idea persists as a careful note of humility. Cosmology is empirical. Its confidence is the confidence of instruments and cross-check sky maps. If they ever point elsewhere, the story will bend with them. A subtler uncertainty lives in the stability of the fields that fill space. The Higgs field, which grants mass to particles, might be balanced in a state that is deeply long-lived but not absolutely final. If so, a quantum event could, in principle, seed a bubble of a truer vacuum, expanding at near light speed and altering the laws within. The best calculations place such lifetimes beyond any practical horizon, folded into the same near eternity as heat death itself. It is a possibility to acknowledge and then to set gently aside. Closer to the bedrock of matter, another open question waits: the fate of the proton. Some grand unification ideas predict that protons are not perfectly stable, that given enough time they decay into lighter particles. Experiments have not seen this decay, they only keep extending the minimum lifetime, already far beyond the age of any star. If protons do decay, the universe will eventually shed its last solid structures into a fine rain of radiation and neutrinos. If they are stable, matter can persist in ever colder and lonelier forms. In both cases, the direction points toward a smoothening, not a storm. When the last black hole fades, when the last slow decay has finished its sentence, what remains is a thin bath of low-energy photons and the faintest relic particles, spread across a space that keeps on widening. The temperature is so close to zero that numbers lose their usefulness. The differences that once drove stars and storms are gone. It is not a dramatic silence, only an even one. The universe has not failed, it has completed its work of evening its contrasts. This is the ending that fits our best measurements. Not a catastrophe, but a settling. It is far beyond the lifetimes of galaxies. It is beyond the lifetimes of the words we use to measure lifetimes. In that distance, fear dissolves. There is no hurry here and nothing to rush toward. The cosmos does what all systems do when left to themselves. It explores its gradients and spends their difference, then it rests. If the margins of the map ever move, if dark energy reveals a hidden turn, if a field proves less stable than we believed, then the ending changes with them. For now, the main line of the story is the long cooling. The fabric widens, the contrast softens, the bright engines run down by laws we understand well enough to trust across time. The universe, having made stars and chemistry and thought, becomes even and still. Let that be a calm image, not a bleak one, a great sea whose waves have slowly lost their sharpness, leaving a surface without strain. Somewhere inside that history, we had our brief epoch of brightness, and we used it to look outward and understand. Nothing takes that away. The far future keeps its cadence unbothered and sure, while we live our warm interval within it, listening to the slow tide and resting in the knowledge that endings too can be gentle. As we continue through our voyage, let the mind uncoil. We are going to listen for the simplest rhythm the universe keeps, a soft accounting that turns difference into balance and busy motion into rest. Entropy is the measure that keeps this ledger. It does not judge, it counts. When possibilities are many, entropy is high. When possibilities are few, entropy is low. The story of time as we feel it is the story of systems moving from the special to the ordinary, from tidy arrangements to those that can be realized in countless ways. Imagine a jar of colored beads. Shake it once and the beads tumble into a new arrangement faster than you can track. You do not follow each bead, you see only the overall pattern. Most shakes produce a well-mixed jar, almost none produce tidy stripes. The reason is probability. There are far more ways to be mixed than to be neat. Entropy is the number that favors the mixed state, not because the universe prefers disorder, but because the mixed state can be achieved in so many more microscopic arrangements. Physicists give names to these layers of description. A microstate is the exact bead-by-bead arrangement of the world. A macrostate is the broad picture you see without a magnifying glass. The second law of thermodynamics says that a closed system drifts toward macrostates that can be made from more microstates. When there are many more ways to be even than to be uneven, evenness wins, slowly, patiently, and almost always. Heat flows from hot to cold for the same reason. A warm stone placed in cool water shares its energy until both meet in the middle. The ability to do work, running an engine, building a cell, depends on those differences. That usable portion is called free energy. As differences fade, free energy is spent. Entropy rises. The shoreline of possibility smooths. A famous thought experiment tries to cheat this tide. Maxwell imagines a tiny demon controlling a door between two rooms of gas, letting fast molecules go one way and slow molecules the other, conjuring a temperature difference for free. The resolution is quiet. To sort molecules, the demon must measure and remember them. Recording and erasing information has an energy cost in our world. That cost shows up as heat elsewhere. Cleverness does not escape the bookkeeping. Information and thermodynamics are bound together. Knowing has a price. Another gentle idea explains why we feel an arrow in time. Coarse graining is the decision to ignore the smallest details. You describe the colours of the beads, not each bead's exact position. When you average over fine structure, only the most probable patterns remain visible, and those trends lead toward equilibrium. Stir two paints and the swirls fade into one colour. In principle, the swirls could return, but that would require reversing every tiny motion at once, an arrangement so special that nature almost never stumbles into it. The arrow we feel is born from probability and from what we can realistically observe. In ordinary life, we call entropy disorder, but a better word is multiplicity. It counts how many detailed ways a broad state can exist. A shuffled deck feels more random than a perfect run, not because the physics has changed, but because there are astronomically more shuffled orders than strict sequences. The second law is, at heart, a law of counting. Gravity complicates the picture without breaking it. For a gas sealed in a box, the most probable macrostate is smooth and spread out. Under gravity, structure forms. Clouds gather, stars light, galaxies braid themselves into spirals. Clumping looks like the opposite of smoothing, yet gravity still drives entropy upward. There are far more ways for matter to arrange itself into intricate, lumpy structures than to preserve a perfectly even smear. As clumps grow, they radiate energy away, allowing tighter structures and opening still more pathways for the remaining pieces to arrange themselves. A universe once smooth finds countless ways to be richly patterned. This is why the early cosmos is thought to have begun in an extraordinarily low entropy state despite being hot and uniform. Smoothness under gravity is special, like balancing a marble on a hilltop. A tiny nudge sends it rolling into valleys of structure where it can rest in innumerable arrangements. As the universe expanded and cooled, Small ripples in density grew into galaxies and clusters. Radiation carried excess energy away. Entropy climbed. Black holes reveal how tall this climb can be. They're not merely dense, they are the most generous keepers of entropy we know. A black hole's entropy scales with the area of its boundary, the event horizon, rather than the volume inside, tying thermodynamics to geometry in a way that still feels surprising. In simple language, a black hole can encode an enormous number of microscopic possibilities, far more than a star of the same mass. When matter falls in and the horizon grows, entropy rises by amounts that dwarf ordinary processes. The universe seems to funnel complexity toward horizons, increasing the count of ways its details might be arranged. And yet, even black holes are not final. Quantum fields near their edges allow them to lose mass through a faint glow called Hawking radiation. For large holes, that glow is unimaginably slow, but patient arithmetic welcomes slow. Over spans of time that bury numbers in forests of zeros, black holes shrink and vanish, returning their stored energy to space. Entropy still climbs, because the radiation spreads into an even thinner, more numerous set of possible states than the compact object that preceded it. Life takes its place in this same accounting. A star shines, space is cold, a planet in between can run chemistry by letting energy flow from source to sink. We are not exceptions to the second law, we are its artisans. By exporting heat to the night, living systems maintain small pockets of low entropy while raising the entropy of their surroundings by a larger amount. A city at dusk is a map of this flow, light and warmth spilling outward, equilibrating the day's intake from the sun. Order is local and temporary, paid for honestly by the whole. As expansion continues, the big gradients thin. Starlight weakens with distance. Star formation dwindles. The cosmic background cools. Free energy grows scarce. Engines, biological or mechanical, struggle to find both fuel and a cold sink for their waste heat. The long winter is not an event, but a tightening of options, like a music box winding down until the last notes are too soft to hear. Entropy does not mean chaos in the noisy sense, it means the settling of differences. It is the quiet preference for arrangements that can be realized in many ways. That preference gives time its direction in daily life, from melting ice to a galaxy's gentle aging. It does not forbid local order, it only asks that when all flows are counted, the total balance leans toward evenness. There is a humbling symmetry in all this. The arithmetic that lets a cell fold a protein also ensures a star spends itself and a galaxy dims. The universe makes patterns, uses them while energy can flow, and then smooths them away. Each step is lawful, unforced, and in its way, kind. Hold one picture softly, a field after snowfall, footprints disappearing as fresh flakes fall, the surface becoming whole again. The second law is the sky's version of that snowfall. It does not rush, it does not punish, it completes. Keep this arithmetic at the back of the mind like a steady pulse. In the chapters to come, we will watch how stars, worlds, and black holes trace this law across time, and how the far future becomes a place where almost nothing is left to push against anything else. The universe leans towards balance, and we are fortunate to live during the hours when the music is still playing. Now I want you to picture a slow snowfall across the sky, a hush that arrives not with cold, but with time. There was a bright noon in the universe, a season when new suns kindled by the millions each year, when galaxies fed on rich rivers of gas and scattered blue light like frost. That noon has passed. Starbirth is gentler now, more selective, as if the cosmos has moved from busy harvest to careful gardening. The long winter does not arrive as an event. It settles by degrees, one nebula quieting, then another, until the night glows with endurance rather than growth. Stars begin in dark nurseries, clouds of molecular hydrogen, cooled by dust and whispering molecules. Gravity finds the denser knots, leans on them, and the knots give way, tightening into cores that warm as they shrink. When the center grows hot and pressurized enough, hydrogen fuses into helium. A lifetime opens with that first ignition, sustained by a precise balance. Fusion pushes outward, gravity pulls inward, and the star learns to stand between the two. The family of stars is wide, and the smallest members are the most numerous. Astronomers call this tilt the initial mass function, a quiet preference for low mass. Mass is a clock. Blue giants spend fuel like a bonfire, brilliant and brief. Suns like ours pace themselves for billions of years. Tiny red dwarfs sip their hydrogen so slowly that their lifetimes reach into the trillions. They are cooler, their pressures lower, their cores unhurried. Many are fully convective, mixing hydrogen from surface to center, so no fresh fuel is trapped out of reach. A red dwarf glows like an ember that never threatens to gust. None has died yet, because the universe is not old enough to see one finish. Fusion follows different routes depending on the weight of the star. In stars like the Sun, the proton-proton chain stitches hydrogen into helium with patient steps, releasing light and neutrinos as receipts of progress. In heavier stars, carbon, nitrogen, and oxygen act as catalysts in the CNO cycle, quickening the burn and the brightness. When central hydrogen dwindles, the balance shifts, the core contracts and heats, the outer layers swell. A star like ours becomes a red giant and learns a new craft, fusing helium into carbon and oxygen. Very massive stars move through further chapters, building heavier elements until they reach iron, which pays no energy back. Then support fails. Some finish as generous explosions, seeding galaxies with the elements that make planets and life. Others collapse into neutron stars or black holes, compact lighthouses, and dark anchors in the night. In winter, the balance sheet changes. Gas grows scarce inside galaxies because previous generations locked it into stars, or heated and pushed it outward. The great filaments that once fed galaxies thin as space expands, and the trickle that remains is often too warm to settle. Star formation does not cease everywhere at once. It flickers in small pockets and fades. Think of a city after a storm. Lights winking out neighbourhood by neighbourhood while a few workshops still glow. Worlds ride along inside this change. Around red dwarfs, habitable zones huddle close. These stars flare more than suns like ours, yet they calm with age, and they endure so long that whole histories might unfold around them. Planets migrate, some fall inward, some scatter outward, some are ejected entirely and drift as solitary wanderers, warmed only by their own slow heat and the quiet press of radioactivity deep inside. Remnants multiply as the bright population ages. White dwarfs, the carbon-oxygen hearts of ordinary stars, cool and fade. Their matter is supported not by heat, but by electron degeneracy pressure, a quantum rule that says identical particles resist sharing a state. As they cool, their interiors crystallize. The word is literal. Atoms settle into a lattice under intense pressure, and the star's heart becomes a slowly growing diamond of astronomical size. Neutron stars keep their density and spin like patient gyroscopes. Beams sweeping the dark, their rotation slows, their magnetism eases. Black holes hold what has fallen, quiet for ages, fed now and then by a drifting cloud or a passing star. They rule nothing, they persist. Across trillions of years, galaxies rearrange themselves. Many small encounters add up. Some stars are nudged outward and escape, others sink inward toward the central mass. Binaries surrender energy in close passes and tighten their orbits. Some merge in brief, bright flashes, others spiral together until gravitational waves carry away the last of their motion. Familiar structures keep their identities for a long while, then loosen. Clusters evaporate. Spiral arms fade without fresh gas to sketch their arcs. Ellipticals relax into smoother spheroids. Great patterns become memories sculpted into the distribution of old light. White dwarfs continue their descent towards blackness. Faint embers slip beyond ordinary eyes. In speculative pages written for very distant futures, the densest husks may, after unthinkable spans, ignite rare fusions under crushing pressures and flare once more. Whether such black dwarf supernovae ever happen is a question folded deep into physics and time. It belongs on a far shelf, acknowledged and left there. The last new stars may not be born from clouds at all, but from meetings. Two brown dwarfs, each below the mass needed for sustained hydrogen fusion, can collide and merge. Their sum may cross the threshold and light. These births would be rare and quiet, sparks when winter logs settle. They add little to the ledger, yet they remind us that even late in the night, simple rules can surprise. Stay with the red dwarfs a moment longer, because they are the heartbeat of this season. A star much smaller than the Sun remains fully convective. It never builds a spent core surrounded by fuel it cannot reach. Hydrogen mixed throughout continues to feed the central fire. The light stays steady, the colour warm, the surface mostly peaceful. Models suggest lifetimes of 10 trillion years or more. By then, constellations will have changed beyond recognition, and such a star could still be in early middle age. Their patience comforts. The sky will not go dark suddenly. It will rest on shoulders that know how to wait. If you could sit beneath that future sky, it would feel familiar and strange at once. The Milky Way, long since merged with Andromeda, would be dim and altered, its spiral phrases softened into a broader glow. Bright blue stars would be gone, their short songs finished. The night would be salted with deep red points and quiet embers, many too faint for human eyes without help. Now and then, a nearby white dwarf would wink with a ghostly gleam, like a coal under glass. Somewhere far off, a neutron star might pulse, a metronome in an empty hall. On larger scales, galaxies drift apart, not within their own bindings, but in their relationships with distant neighbours. The space between clusters widens. Light that once crossed easily now stretches into longer wavelengths and slips from view. The local group remains together. The merged Milky Way Andromeda system carries its stars forward in a shared tide. Within this sheltered region, the long winter feels like a sustained hush rather than a loss. Chemistry changes with the ages too. By that time, metals in the astronomical sense, elements heavier than helium, are more common in the gas that remains. Worlds built from such material could be rich in rock and complex chemistry, yet poor in water and light unless fate places them well. It is possible to imagine slow ecologies under red suns or beneath thick ice, powered by modest gradients that would seem austere to us and sufficient to those who know nothing else. The universe makes use of what it has. As winter deepens, free energy becomes scarce. Engines of every kind begin to struggle. Star formation ceases not because the rules have changed, but because the raw materials and the necessary contrasts have thinned. Heat can no longer find the cold sink it needs in the right amounts. Cold can no longer find the warmth it needs to build motion. What remains is endurance. Objects that can last. Processes that demand generous gradients fall silent. Return to snowfall. Footprints soften, edges blur, the field becomes whole and smooth. In thermodynamic language, microstates multiply for macrostates that are even, and the universe prefers them by counting alone. This is not cruelty, it is completion. The long winter is the night's way of finishing a melody that began when hydrogen first learned to glow. You can hold all of this without weight. Nothing here demands urgency. We live in a bright interval, early in the story, with blue stars still singing, and rivers of gas still silver in the dark. Our tools let us look forward by law rather than wish, and what we see is a future that settles, not one that breaks. Later chapters will dim even the red embers, and the quiet will grow deeper than any night we know. Before we reach them, pause here, where light still has patience and the sky keeps its slow work. The winter will come, it will arrive with grace, and for a very long time yet, the stars will keep us company. Imagine a star that has finished its bright speaking and learned to hold its warmth like a coal cupped in steady hands. This is a white dwarf, the ember heart of an ordinary sun. Small as a world, dense enough to bend thought. It no longer burns in the usual way. There is no new fuel at its centre, no steady fusion to push outward against gravity. What holds it up is quieter, a quantum firmness in the electrons themselves, a pressure born of their refusal to share the same state, keeping the star in balance while it shines only with the heat it already contains. A white dwarf is born when a star like ours swells into a red giant, sheds its outer layers into a gauzy shell, and reveals its core. That core is mostly carbon and oxygen in the common case, sometimes blended with heavier elements if the parent was more massive. The nebular glow fades, but the core remains hot and piercingly bright, no larger than Earth yet carrying half the sun's mass or more. Its gravity is fierce, its skin white or blue-white, and its cooling begins the moment it is exposed to night. There is a simple limit to this quiet survival. If the remnant is lighter than about 1.5 suns, electron degeneracy pressure can support it indefinitely against collapse. This boundary is the Chandrasekhar limit, a name for the point where quantum rules meet weight. Above that mass, the scaffold yields, and nature chooses a different end, collapse into a neutron star or a black hole. Most stars fall below the limit. White dwarfs are not rare endings. They are the most common bones of starlight in the galaxy. Cooling is their work now, and they practice it for eons. At first, the heat pours away quickly, the surface blazing while the interior rearranges. Neutrinos may carry energy out through the dense matter for a while, slipping through barriers that stop light. As centuries become ages, the glare softens to pearl, then to something only patient telescopes can see. Inside, atoms slow and settle. At great pressures, the matter organizes itself into a lattice. The heart crystallizes. Crystallization here is not metaphor, but phase change, as real as water becoming ice, enacted under gravity so strong that the lattice is squeezed to a fantastical density. When ions lock into place, they release latent heat, a last gentle warmth that slows the cooling and briefly steadies the light. Stellar seismology, the listening to minute pulsations, suggests many white dwarfs already carry crystalline cores, diamond-like geometries, hidden beneath a thin glowing skin. Form follows pressure. Pressure follows gravity. The beauty is simply the physics made visible. As the dwarf cools, heavier elements sink and lighter ones float, a quiet sorting that changes the surface chemistry we can read. Hydrogen can collect as a thin, clear atmosphere. Helium can settle just below. Deeper still, heavier ions hold the remaining heat. The star's colour slides from white to yellow to red, then slips beyond red into wavelengths too long for human eyes. No combustion drives the glow. What we see is a long exhale of stored heat through a surface that grows ever less willing to radiate. Time in this chapter swells beyond ordinary sense. To grow dark to human sight takes longer than civilizations last. To cool near the temperature of the cosmic background takes longer than galaxies remember their shapes. The universe must make room for such patience by expanding and thinning so that the background light drops and stops reheating the ember. Cooling is a race the dwarf wins only because its opponent, the sky itself, grows colder with it. Around many such embers, planets still move. Some survive the red giant storm and are refitted into new orbits by tides and winds of gas. Others arrive later, nudged inward by the slow shuffle of an aging system. We have watched planets transit white dwarfs like moths crossing a small lamp. We have seen rocky material in dwarf atmospheres, a dusting of planetary ash that sank from disrupted worlds. In the long winter, these become slow, intricate clocks. Asteroids wander, comets return, rings of fine debris sift inward and vanish. The star, mute and compact, keeps time for them all. Thresholds hide in the details. A dwarf that gains a trickle of matter from a companion can flash in a nova, a temporary brightening that paints the dark with brief fire. These are resets, not rebirths. They do not reverse the cooling. They only mark it with fading spikes. If two dwarfs merge, the sum may cross the mass limit and collapse or ignite, returning heavy elements to space. Such late dramas will grow rarer as the universe settles, but patience keeps the possibility alive. The cadence slows as ages deepen. Early in a white dwarf's life, 1,000,000 years can lower its temperature by tens of thousands of degrees. Later, 1 billion years barely nudges the thermometer. Heat sinks into the crystal. The surface grows more opaque to its own radiation. The exit lane narrows. The star becomes a dark cherry, then a coal in ash, then a memory that still glows in the infrared. Touch is out of the question. A pebble dropped from a modest height would strike with the force of a bomb. The surface is smooth in a way only pressure can make smooth. Far beyond any age we name, the light slips beneath the gentlest instruments. By custom, we give a new name then. A black dwarf is a white dwarf cooled until it no longer shines with its own heat, its temperature nearly indistinguishable from the background. No one has seen one. The universe is too young. Yet the same physics that carries white dwarfs downward will carry them all the way, given time. The name is a placeholder for a certainty. What, then, is a black dwarf like? Picture a sphere the size of Earth, utterly dark to human eyes, warm only by a whisper. Its interior is a solid lattice under impossible squeeze, its crust a thin veneer of lighter atoms, its gravity a wall around every step. It makes no light of its own and reflects little of what falls upon it, for almost nothing is left to fall. It is, in a strict sense, finished. Even finished things can surprise. Some calculations suggest that in these deep futures, pressures in the crystalline heart may enable rare fusions that were impossible when the star was brighter and softer. Nuclei brought close by the lattice might tunnel together, releasing small pulses of heat and changing the composition by degrees. In imaginative but careful work, very massive black dwarfs may eventually assemble enough iron to trigger a final collapse or explosion. These ideas live at the edge of theory and on timescales where language stumbles. Hold them loosely. Their lesson is simple. Even the ash of stars is not entirely idle under gravity's hand. If protons decay, the lattice will one day unweave into lighter particles that drift outward as faint radiation. If protons do not, the black dwarf can persist, an object defined by endurance rather than change. In either case, history leans toward evenness. The dwarf is part of the great smoothing entropy, right across the sky. It is tempting to call this ending bleak, but held gently it offers a different mood. White dwarfs prove that stars do not waste their light. They store it, release it slowly, and pass it back to the night as warmth rather than flame. The path from white to black dwarf is not failure. It is the completion of a story fusion began. The carbon and oxygen within were forged in earlier fires, perhaps in rings blown from a red giant, perhaps in shells that once lit a small system with ruby light. And those atoms will persist, whatever their final packing, long after constellations forget their names. In the broader cosmos, the age of Embers is an age of memory. Galaxies will carry fewer new songs and more long notes. The bright extravagance of blue giants gives way to the patience of red dwarfs and the silence of finished cores. The night becomes fuller of endurance than of events, and in that endurance there is calm. Hold one last image, a shore after the tide has gone out. Wet sand, faint ripples, shells arranged by a slow hand. A white dwarf is such a shell, intricate and solid, shaped by many hours of water and sun. A black dwarf is the same shell in starlight, so soft it is nearly no light at all. Its curves still present, its story complete. We live in the warm, middle chapters, and that is a gift. To know embers is to respect the day. To know ash is to see how faithfully the universe keeps its accounts. Ahead lie chapters on the reign of black holes, and the thinnest lights of all, where even the keepers of gravity learn to fade. For now, rest in this knowledge. When stars finish, they do not vanish in despair. They become precise, enduring things, cooling with grace until the night, and they are almost the same. We have walked through the cooling of stars and the patience of embers. Now we arrive at the keepers of deep time, the objects that finish what gravity begins and wait while the universe grows old around them. A black hole forms when matter is pressed past every ordinary support. In a massive stellar core, fusion fails to pay its bills, gravity tightens, electrons and then neutrons surrender their pressure. Collapse carries the heart inward until a boundary appears that no light can cross again. This boundary, the event horizon, is not a surface in the usual sense, but a one-way shoreline drawn by geometry. Inside that line, every path curves toward a centre that shortens distance the way a whirlpool gathers water. Outside, space is altered too, though more gently, as if the field has learned a new steepness. There are several paths to such an object. The common one is the death of a heavy star. Another is the silent birth of a giant in the early universe, when large clouds fell straight in and planted massive seeds in young galaxies. From there, growth is patient. Gas spirals inward and heats, giving back part of its energy as light before it slips below the horizon. Stars that wander too close are pulled into long threads. Their pieces turn to soft radiation as they fall. Later, as galaxies merge, their central black holes meet and orbit, the dance tightening, while space-time carries energy away as a faint rippling wave. Those mergers write a quiet music into the background of the cosmos, a bass line you cannot hear, though instruments we built have begun to feel it. With each meeting, the horizon swells, and with each swelling, the book of entropy turns another page. Black holes are not only dense, they're generous in how they count possibilities. The number of microscopic arrangements that can give rise to a given horizon scales with the horizon's area rather than the volume within. Thermodynamics and geometry meet there, and the meeting implies a temperature, tiny for large holes, that lets them glow and slowly lose mass. Small holes are warmer, large ones are colder. The giants at galactic centres drink the night and leak almost nothing back for intervals longer than galaxies can measure. In the long winter, this arithmetic rules. Where gas remains, a central hole can flare with accretion and then settle. Winds and thin jets from that feeding push on the surrounding medium, sculpting the last reservoirs of star-making. When the gas thins, feeding becomes rare. A stray star arrives and is torn apart. Then nothing happens for a very long time. The hole waits. Around it, the galaxy ages. Gravity keeps rearranging the furniture. In dense clusters, many small encounters add up to changes in orbits. Light stars are tossed outward, heavy remnants drift inward. Some stars are ejected entirely and leave the galaxy with a little surplus speed. The central mass grows by small tastes and by occasional feasts when two black holes finally meet. The merger shakes the fabric of space with a single, deep pulse. The remnant recoils a little, then resettles. Horizon area grows with each event. Entropy climbs with it, keeping faith with the quiet rule that the universe prefers the states that can happen in many ways. As time opens, black holes become the principal banks where mass is stored. Stellar remnants that did not collapse still persist, but their share of the ledger shrinks. Supermassive black holes at the hearts of merged galaxies carry millions or billions of solar masses. They are the anchors of the last great systems. As thermodynamic objects, they're cold, and their evaporation is so slow that the word slow feels fast beside it. The years climb by powers until counting looks like a forest of zeros, a landscape where the mind walks a few steps, smiles, and sits to rest. Even in that age, something continues to happen. The smaller holes vanish first, returning their mass as a thin glow that warms nothing. Stellar mass holes follow after spans that make the age of stars feel like a morning. The largest ones endure the longest. They are winter mountains, dark and still, eroding grain by grain into light of ever lower energy. At first, the radiation is the faintest of embers. Later, as the whole shrinks and warms, the glow sharpens for a moment. Then it is gone, and the account on that object closes. The information they swallowed remains a tender question. Many think no information is truly lost, that the final radiation must carry subtle patterns reflecting what fell inside. Others explore models where the accounting is stranger, yet still lawful. This is a gentle margin on our map, a place where rules we trust meet a quantum shore we do not yet resolve. For our purpose, the rhythm does not change. Horizons grow with mergers and feeding. Total entropy increases, and in the end, a horizon fades and returns its store to space in a way that leaves the whole more even than before. Spin adds small textures to the picture. Material that falls in can wind the whole up. That spin stores energy that magnetic fields in the surrounding plasma can tap. When spin is high, narrow jets pierce the dim galaxy, thin beams writing lines across a quiet sky. These are local weather in a very large climate. They shape nearby gas for a while, then they end, and the climate goes on. Imagine the distant fate of our local group, long after the Milky Way and Andromeda have merged. The centre likely holds a single, enormous black hole. The orbits of nearby stars thin through encounters. The diffuse halo drifts outward. The outskirts forget they were once part of a disk. A few long-lived red stars wander on wide paths, and then finish, becoming white dwarfs and later black dwarfs, while the central mass sits in its steady well. Eventually, even those remnants are scattered away or swallowed. The centre remains and watches a quiet sky. On timescales beyond these scenes, black holes are the last engines that still have work to complete. They turn mass into low-energy quanta with exquisite patience. They are the final way the universe spends stored difference in a world where almost every other gradient has gone flat. Their work is not violent then. It is a balance sheet closing on its last column, a slow transfer of energy into the thinnest possible form. Side notes do not change the melody. If protons decay, the sparse matter between islands fades more quickly into radiation, and the supply of meals ends sooner. If protons are stable, small pockets of matter endure longer, but their part in the total is minor by then. Dark matter, if it does not annihilate or decay, lingers as a dilute halo, lightly bound to the deepest wells, and easily lost as expansion continues. Black holes hold what remains, then they evaporate, then there is less to hold. Return to feeling. The black hole age is not a storm, it is a settling. There are fewer bright edges, fewer shocks, fewer surprises. The rhythm is long and even. Large things finish becoming simple. The horizon, once a dramatic idea, becomes an everyday feature of the last architecture, then a memory, then nothing at all. When the last of them goes, the universe will have let its strongest gravity wells unwind into the softest light. No object will remain that can bottle energy away from the evening of contrasts. What fills space then is thin radiation and rare light particles, spread so evenly that hot and cold have little use. That is the threshold of the next chapter in our journey, the time after the last light, where the cosmos keeps expanding and the temperature keeps falling, and the story continues with the same quiet law. For now, rest with this picture, a sky grown spare, a few deep wells that keep time for everything else, a long patience that neither hurries nor stops. The black hole age is the universe learning how to finish its accounting, and it does so with the same calm that brought stars to life and carried them to rest. Allow yourself to drift slowly. We have passed the age of stars, then the age of embers, then the long patience of horizons. What remains is the thinnest weather a universe can keep, a faint wash of radiation, a handful of almost weightless particles, and space itself, widening without hurry. The backdrop is cold. Every photon that ever crossed a distance has stretched with the expansion, sliding to longer and softer wavelengths. What was once a bright microwave glow becomes radio, then a whisper with a wavelength larger than galaxies. Neutrinos, shy travellers from the hot beginning and from every furnace since, slip onward, noticing almost nothing as they pass. If instruments could be tuned far beyond any we know, the scene would lack edges. It would feel like standing in a spacious dusk that never changes, a dusk without a sun. In this era, the universe is a nearly perfect equalizer. Differences, the very contrasts that once ran stars and storms, and chemistry and thought, have been spent. Free energy, the ability to do work, is almost gone. Engines cannot find a warm place to draw from, and a cold place to give back. The music box has wound down. What continues, continues, because nothing is left to stop it, not because anything is left to drive it. There are still actors on the stage, but they are quiet ones. If protons decay, the last stubborn bits of matter have long since become lighter particles, feeding the thin radiation that fills space. If protons do not decay, a few frozen relics endure, but they are sparse and slow, scattered across distances so large that meetings become miracles of chance. Dark matter, if truly stable, lingers as the faintest halo in the deepest wells, or else drifts outward until even gravity loosens its hold. Across the widening, almost nothing binds for long. If dark energy remains constant, as the best measures suggest, the universe approaches a steady kind of emptiness. Not a theatrical void, but a near unchanging climate, with a temperature so small that numbers struggle to describe it. This climate belongs to horizons. In such a cosmos, every observer lives within a limited patch whose rim is a horizon drawn not by walls, but by acceleration. Beyond that rim, light cannot arrive. Within it, light still circulates, although ever more softly. Even emptiness has a temperature here, a gentle thermal bath set by the horizon itself. You cannot feel it, yet it is present, as reliable as geometry. Horizon can sound severe, but here it is only a boundary of knowledge. Inside the patch, everything that can interact does, until there is nothing left to trade. Entropy, the count of ways the details can arrange themselves, climbs as far as it can within that domain. This is the plain meaning of heat death in an expanding universe, the evening of every remaining contrast, limited only by what can talk to what. Small and delicate happenings persist. Electrons and positrons, if any remain free, drift so slowly that attraction can coax them into positronium. Improbable atoms, with sizes greater than many stars once were. Their orbits are languid, their lifetimes long. In the end, they meet and annihilate, and each event joins the faint river of light. Rare collisions still occur in the depths between islands, turning matter into radiation and radiation into matter, back and forth, but always trending toward thinner balances. Each event is a notation in a ledger that has almost ceased to change. The language of this time is redshift and patience. Waves recede, distances grow, local pockets relax into the most probable arrangements, and those arrangements are even ones. It is no longer a story with chapters and turns. It is a plateau so broad that the idea of a turn becomes a private joke among numbers. When people once said forever, they meant something like this, though they could not have guessed the shape. Listen more closely, and there is a further quiet. Quantum fields, the undercurrent of reality, still ripple with tiny fluctuations. Most are so modest that they cancel and vanish like rings on a lake after a windless night. A few, in theories that allow it, may kindle brief, local patterns. Never enough to rebuild the old order, only enough to remind us that nothing is perfectly still at the smallest scales. More speculative pages imagine that, given enough time and a horizon with finite entropy, rare occurrences could mimic pieces of the past, echoes that look briefly like order and then wash away. These ideas live at the polite edge of what we know, and their timescales are so vast that saying them aloud changes nothing. Hold them loosely and let them drift. What matters for feeling is completion. The universe has spent its differences honestly. Every gradient that could run an engine has run it. Every store of mass that could be turned into thinner light has been turned. Even the greatest vaults, the black holes, have balanced their accounts, releasing their hoards as a final warming sigh before going silent. What remains is not a ruin, it is a balance sheet with no numbers left to change. From within such a future, the past would be a myth told by the thin radiation itself. Its spectrum carries memories of the hot beginning, of the era when electrons and protons first joined, of ages when stars lived fast and left generous ashes, of the long dominion of horizons. Neutrinos keep their own version of this archive, a private record of the early universe and of every collapsing heart. No mind reads these histories now. Reading needs gradients as well. Yet the records exist in the way they must, as patterns etched into the distribution of energy, as a texture in the cold. You can ask whether time still deserves its name here. It does, but not the kind that once grew forests and cities. It is the soft tick of expansion and the softer drift of wavelengths to longer lengths. It is the aging of a temperature that scarcely changes. It is the arithmetic of waiting in a place where almost everything that could have happened already has. This is the true face of the gentle ending, not darkness as a threat, but darkness as an evenness so complete that light has nowhere in particular to go. There is almost nothing left to push against, almost nothing else. Space keeps widening. The bath keeps cooling as far as the horizon allows. Within each patch, the last traces of structure are diluted until even the words structure and trace become ceremony. If you want an image to keep, let it be simple. Picture a broad plain after snowfall, unmarked, extending in every direction, quiet beneath a sky of slow colour. Stand there in thought for as long as you like. Nothing intrudes, nothing hurries you along. The silence is not empty. It is full of everything that has finished happening. From this stillness, the mind will naturally wonder about other endings, sharper turns, sudden weather. We can visit them gently. A universe that could tear its own weave if the pressure that drives expansion grew with time. A universe that could reverse and fall inward if the outward push softened and gravity reclaimed the lead. A vacuum that might, in principle, choose a deeper state and retune the rules within it. Keep those doors in view, but hold for one more breath to the quiet you have now. It is the most likely answer to the question we began with. It is the evenness toward which every chapter has leaned. The night is very old, the differences are gone, what remains is rest. Relax into an easy breath and picture the fabric of space as a quiet sheet stretched on a frame. Most nights it loosens, almost imperceptibly, the way cloth relaxes on a line. But there is a speculative page in the sky's ledger where the loosening is not gentle, the pull sharpens with time, drawing not only between galaxies but, if carried to its end, between the parts of things themselves. Cosmology gives this imagined future a simple, dramatic name, the Big Rip. Begin with pressure. To describe the character of whatever fills space, physicists use a single ratio that compares pressure to energy. When that ratio rests at -1, the effect behaves like a steady feature of the vacuum. Dark energy is a calm push that accelerates expansion without changing its strength. If the ratio dips below -1, the push grows as space grows. Expansion feeds on expansion. Interest is paid on interest continuously, and the rate itself edges upward. This more than gentle pressure is often nicknamed phantom energy. The name is theatrical, the idea is plain. As the universe stretches, the very thing driving the stretch becomes stronger. Pull on the fabric, and the fabric pulls back harder. Geometry answers by widening faster still, and given enough time, the widening runs to completion in a finite span rather than trailing off forever. There would be a countdown of sorts, beginning so far beyond our era that counting it would feel like poetry instead of policy. Because gravity binds, the unmaking would not arrive all at once. It would work down the hierarchy with eerie patience. first the loosest ties yield, clusters of galaxies held by the weakest large-scale bonds, unspool and drift. Later, as the pressure steepens, individual galaxies lose their shape. The orbits that once kept their stars in quiet swirls become impossible to maintain. Later still, stars and planets surrender their ellipses, rings dissolve, moons wander, binaries part. Close to the end, even the forces inside matter begin to notice. Molecules let go, then atoms, and finally, the tightly bound cores of atoms find no refuge. The tempo quickens from eons to years to days to moments. This is not the favoured forecast. Today's measurements lean toward the steadier case. The pressure appears very close to the simple value. Yet the error bars still have width, and honesty asks us to walk this path once with soft steps. The Big Rip is a thought experiment made from numbers we do not yet know exactly, and from physics we pencil in at the edges. We visit it not to frighten, but to understand what more negative pressure would mean if it were carried to its logical end. Seen from a safe imaginary distance, the pictures are oddly quiet. There is no single explosion, no flame, only a growing inability for structures to remain themselves. A galaxy becomes a halo, then a mist. A solar system becomes a tangle of unbound lines. A planet becomes material, then, very briefly, a light. What held together unholds, not from a blow, but because the background rules have tilted past the point where holding is possible. The universe chooses simplicity over architecture. It is natural to ask what kind of substance could make this happen. Here the physics grows careful and modest. The simplest models that push the ratio below -1 often suffer from instabilities. Treated too literally, they can assign negative kinetic energy to a field, inviting unphysical cascades. More refined constructions try to avoid those pathologies, or arrange that the phantom behaviour appears only in the way cosmic distances add up, not in the way particles behave in a laboratory. In short, the Big Rip asks the cosmos to be stranger than we see anywhere else, and yet not so strange that other, well-tested corners of physics fall apart. It is a narrow bridge drawn in faint chalk. There is also an observational way to phrase the same caution. Suppose the pressure does slip below the steady value. Does it stay there, or drift back towards calm? If it approaches -1 from below, the future is less dramatic. If it keeps dropping, the future tightens. Our instruments narrow the possibilities and, for now, whisper that the steady case still fits well. They cannot banish the phantom entirely, but they do leave the door only barely open. What would the rhythm feel like, living inside such a history? For almost all of it, nothing would seem different. Galaxies would age, stars would form and fade, civilizations, if any persisted, would write local stories under skies that gave no special warning. Only much later would the widening take on urgency, and then the long steps would shorten. A quiet tidal strain would become a noticeable drift. Orbits would precess with a stubbornness no correction could tame. Architectures we considered permanent would reveal themselves as temporary agreements. It is unsettling, but also orderly. The cosmos would not be capricious. It would be consistent to the end. There is a tender irony in the final scene. The same expansion that once cooled the hot beginning and made room for atoms and stars would, in this path, erase them. The same mathematics that granted galaxies the space to blossom would unweave their petals. The universe would complete a kind of circle, not by returning to where it started, but by using the same instrument in two keys. First to separate and cool, then to separate beyond repair. Hold the idea lightly now and return it to the shelf. Its value here is contrast. It teaches how sensitive the far future is to the exact character of the pressure in space. A shift that looks small in a symbol, less than a single digit away from the steady case, becomes vast when multiplied by ages without number. Cosmology is like that. Tiny tilts in the rules, played on the instrument of deep time, yield very different melodies. It also reminds us of scale. Gravity binds with devotion at close range. It knits stars and stones with threads stronger than any wind. Only a truly global change in the background, a rise in the outward push of space itself, could persuade those bonds to yield. The big rip is that persuasion carried to its extreme, the universe changing the terms of the debate rather than winning by force at any single place. For our quiet voyage, the most helpful truth remains the calmer one. The best measurements suggest the vacuum's pressure is steady, and the long future is a gentle evening, not a violent unthreading. We live under that expectation, a comforting sky to sleep beneath. But it is good to have visited the other weather, if only to understand the map. Knowing where the cliffs are makes the trail feel safer. Let the breath return to its easy pace. Next, we will turn the question around. What if the widening stops? What if gravity reclaims the lead and the fabric begins to draw inward? We will walk that path as well. A path of reunion rather than rending, carrying the same rule that has guided us so far. Pair each idea with a clear image, keep fear small, and let wonder do the speaking. Picture the universe as a long, slow tide that has only ever flowed outward. Now imagine a night, far beyond any calendar, when the outward slackens, pauses, and begins to draw back in, not with a snap, but with the composed turn of a great wheel. This is the idea of a cosmic reversal, a future where expansion yields to contraction, and the story that began in heat and density returns to them. For such a turn, the balance of energies that shape space-time must change. The push that quickens expansion appears steady today. A reversal would ask that push to fade, perhaps even to become a gentle pull. Some models imagine a field that evolves with time, its pressure shifting as it rolls through a landscape. Others lean on geometry, asking for curvature that eventually tips the sum. The mathematics is careful and conditional. Nothing on the sky now demands a turnaround. We visit the possibility for completeness, and because contemplating a cycle has a quiet beauty of its own. If the turn came, the signs would be subtle at first. The redshifts of very distant galaxies would stop growing, then begin to shrink. Horizon distances would fall. The background light, long stretched cooler by expansion, would stop cooling, then slowly warm as wavelengths shorten. Local galaxies would approach one another more decisively. Gaps between clusters would thin. Regions that drifted apart over eons would begin to share neighbourhoods again. Contraction is not expansion played backward. A warming sky brings new habits. As mean densities rise, diffuse gas that hovered between galaxies starts to condense. Clouds are squeezed by the tightening background. Star formation, dulled by the long winter, kindles in fresh pockets. Galaxies collide more often and merge with less ceremony. Cores grow heavy as black holes swallow companions. Their orbits shrink in deepening wells, while space-time carries away energy as faint, persistent waves. Entropy still rises. The universe does not rewind complexity, it changes the stage on which complexity plays out. The background temperature becomes the metronome. Early in contraction, the change is slight, like coals finding a new draft. Later, as densities climb, photons jostle matter more often. Atoms rattled by light give up their bonds. Molecules that endured in the cold fall to pieces in the heat. Eventually, the background warms enough that neutral atoms cannot exist. The cosmos returns to a charged mist, an echo of its younger chapters. Black holes would shape the late reversal decisively. As orbits tighten and galaxies settle into one another, horizons meet and fuse. The largest wells grow larger still. In a contracting world, slow quantum leakage is negligible beside the appetite of infall and mergers. Horizon areas expand, the accounting of entropy climbs with them. Near the end, many separate wells may coalesce into only a few, perhaps into one, a single gravitational depth carrying most of what once was scattered across a sky of islands. The simplest ending writes a stern line, a big crunch. Densities and temperatures rise without bound, distances shrink towards zero, Time, measured by the change of large things, runs itself out. It is the mirror of the hot beginning set at the other end of the book, conceptually clear, mathematically strict, and not at all near. It lies past a horizon of horizons, far beyond any age that touches worry. There are gentler endings on the same inward path. Some proposals offer a bounce, contraction, smooths the universe, then a new expansion begins, passing the would-be crunch without a true singularity. In one family of ideas, the ingredients of the cosmos during contraction act to suppress wrinkles and turbulence, so the approach to the smallest size is calm rather than chaotic. At the tiniest scales, quantum rules add a spring to space-time, preventing infinite compression. The rebound does not erase the past, it initiates a new round. Other visions of cycling are more geometric. They picture a cosmos that, in remote futures, empties itself of rest mass so completely that what remains can be rescaled into a fresh beginning without discontinuity. From the inside, each eon runs from a hot origin to a cold quiet. From an imagined outside, one completed eon hands a smooth boundary to the next. The mathematics is elegant, the image is clean, and the evidence uncertain. That is all right. Sketches are allowed at this distance from shore. There is a brain-inspired rhythm too, where our observable universe is a slice of a larger construction. In that picture, what looks like a bang is a meeting between layers. What looks like long expansion is the slow drift between meetings. What looks like a crunch is not a global failure, but the preface to another gentle contact. The details are intricate, and the proof's not yet in, yet the metaphor is useful. A cosmic heartbeat, quiet and regular on scales, so large that even galaxies are small murmurs within it. Any cycle must make peace with the second law. Entropy prefers to rise, while cycles prefer to repeat. Reconciliations vary. Some dilute old entropy across an ever larger backdrop before a new beginning gathers only a small portion of it. Some allow vast stretches of empty time to smooth the accounts. Some argue that what looks like an increase in one bookkeeping system appears as a reset in another when masses fade and only light remains. The lesson is not which reconciliation wins. It is that any cycle must speak probability truthfully, or it will not sing. What would contraction feel like from within? For most of its long approach, it might feel like nothing in particular. Local systems would remain local. A star would still be a star. A planet would still keep its seasons. Only as the background warmed and distances shrank would universal weather become personal. Long before that, any culture able to measure the shift would have read the signs and written the timing in its books. The cosmos does not change its rules without notice. The rules, patiently applied, carry it from one regime to another. Hold the image of a great breath that has carried outward for ages. In a reversing world, that breath begins to return. It does not erase what was built while it widened. It gathers it, warms it, and writes it into new forms, some brief, some long. Whether the end is singular or cyclic, the modest truth keeps its place. The universe honours its arithmetic. Energy and pressure shape geometry. Geometry shapes history. History is the patient sum of many small lawful steps. We do not know if the tide will ever turn. The maps we trust today point toward continued widening and a gentle evening of differences. Yet there is grace in looking both ways along the shore. The possibility of a return, a chapter that closes and hands a quiet page to another, enlarges our sense of what a universe can be and makes the present more vivid. We live in the outward breath, where stars still light and chemistry still builds patterns that can notice the sky. Rest there for a moment. If the cosmos is a one-way widening, it will end in evenness. If it learns to turn inward, it may gather itself into a final warmth or begin again. Either way, there is no hurry for us. Our small bright hour is enough, and more than enough, to look up and understand. In the next chapter, we will visit a different kind of possibility, one that needs no turn at all. The thought that the vacuum itself might not be final, that a new phase could bloom like frost on glass and retune the rules within its edge, We will approach it gently, honour the distance at which it lives, and then return to the quiet path that remains our most likely future. Imagine that space is not empty, but quietly full. Not full of dust or gas, but of fields, smooth quantities that give every particle its habits. Electric and magnetic fields, the Higgs field that lends mass, the subtle fabric we call dark energy. Each extends everywhere, gentle and continuous, like a faint pressure in the room you notice only when you look for it. Fields can hold energy even when they do not ripple from place to place. That stored energy is a background climate the universe wears without fuss. In simple pictures, a field rests on a landscape of possibility, a surface of hills and valleys. Where it settles determines how much energy the vacuum carries. If it lies in the deepest valley, the vacuum is stable. If it perches on a high shelf or shallow hollow, the state is only metastable, a balance that can last for ages and still not be truly final. Physicists call such a perch a false vacuum. False does not mean wrong, it means temporary in principle, even when the principle plays out over spans so long that counting them becomes an art. From such a shelf, there exists in theory a lower resting place. Reaching it is not a climb, it is a tunnel. Quantum mechanics allows the field to slip through the barrier as if a hill briefly turned transparent. If that slip begins in a tiny patch, a new region appears where the field has found a deeper calm. A boundary forms around the patch, thin and purposeful, separating old vacuum from new. We call that patch a bubble. Inside the bubble, the rules are not chaotic, they're retuned. Energies shift. The constants that once set particle masses and forces may take on new values. Chemistry could be different. The architecture of atoms could be redrawn. What can exist narrows or widens according to the new settings. If such a bubble formed in our cosmos, it would expand rapidly, near the speed of light, driven by the pressure difference between the two vacua. Nothing ahead of its edge would feel it coming. A universe with a speed limit gives no warning. The page sounds dramatic. The physics, in tone, is calm. Calculations within our best models suggest that if our vacuum is metastable at all, its lifetime is breathtakingly long, long enough to overlap with the ages we already call forever. The inputs carry uncertainties. Some theories render the vacuum exactly stable, others keep stability practical rather than absolute. For our quiet voyage, the mood of the evidence matters most. Nothing in the sky asks us to hurry. Hold an image that matches the mathematics. Picture a winter pond under clear ice. In principle, tiny imperfections concede a change of phase, a place where liquid begins again within the solid. If the energy balance favours liquid, and if a small nucleus can overcome the surface tension that resists it, the melt spreads in a widening circle. Now translate the picture. Replace water with a quantum field. Replace temperature with vacuum energy. Replace the pond with the universe. A bubble of lower energy vacuum is like that melt. Except its edge moves not from warmth, but from the field relaxing into a deeper rest. There are delicate variations on the theme. Thermal activation can help fields cross barriers when the background is hot, but our universe cooled past those thresholds long ago. What remains is tunneling, a purely quantum act that does not need heat. Gravity can modify the odds. The geometry of space-time adds terms to the accounting. Some speculative pages ask whether black holes could catalyze a transition, their crowded horizons nudging the field more easily across the barrier nearby. Even there, the numbers that emerge are patient. If there is any risk, it is written in ink, so faint it vanishes into heat, death's timescales. Inside the bubble, the vacuum energy is lower, the local expansion rate may differ, the horizon temperature tied to that expansion may change, particle masses and couplings may be retuned. From the standpoint of inhabitants, if inhabitants could exist in both regimes, the world would not be merely altered, it would be redefined. But that comparison is only a thought experiment. A bubble advancing at near light speed leaves no one to compare notes. It writes a new chapter on a fresh page, and whatever can exist there will exist according to its new rules, without needing permission from the old. Metastability carries a gentle lesson. Nature can be secure for every practical purpose and still not be absolute in principle. Snow can rest on a high slope for years. A glass bottle can hold pressure for decades. A candle can refuse to go out in a still room. Each scene contains an alternative, possible, not demanded, waiting at the edge of chance. The vacuum inherits that character. It is a balance that has endured since the earliest chapters and shows every sign of enduring through the chapters that matter to stars, planets, and thought. In the mathematics of fields, this endurance appears as a barrier in the potential. The barrier has a height and a width. Tunneling cares about both. The exponential suppression is severe. Small differences in the barrier produce enormous differences in lifetime. That is why modest uncertainties in particle masses and couplings become vast uncertainties in the forecast. It is also why the honest summary remains the quiet one. If a transition is possible, it is so rare that it loses all power to disturb a mind-seeking sleep. There is a cosmic echo to these ideas. In many models of the early universe, a field perched high on a plateau rolled slowly, releasing energy that drove a rapid widening of space. In some versions, inflation ends not everywhere at once, but through bubble nucleation. Patches complete their role and ordinary physics begins inside them. Those bubbles expand and may, in certain stories, collide, seeding structure. On that view, our universe is one interior among many. We do not need the claim for our ending chapters. It simply shows how a phase change can write large-scale history with patience instead of drama. Closer to home, the Higgs field is the one most often mentioned in whispers about metastability. Its measured values place it near a boundary between absolute stability and long-lived impermanence. New physics at higher energies, undiscovered, unconfirmed, may move the picture decisively to one side or the other. Until those pages are turned, we hold a sketch and a tone. The sketch says that even if the vacuum is not the final resting place, its next resting place lies unimaginably far in time. The tone says this is a curiosity for thought, not a weather report. There is practical solace in expansion itself. As space widens, the density of everything falls. Any catalyst that might raise the chance of a transition grows rarer. Any thermal stirring cools. The longer the universe lives without such a shift, the lower the hazard per volume becomes in simple models. Patience works in our favour. The future most likely remains the gentle evening we have already described. If a bubble did appear, you might wonder what its edge would be like. Not a wall in the material sense, but a thin region where the field changes value and releases the energy stored in the barrier. That energy emerges as a burst of particles and radiation in the bubble wall, then redshifts and dilutes as the wall races outward. Behind the wall, the new vacuum is calm. Ahead of it, the old vacuum proceeds exactly as before until the edge arrives. No advance sign, no shadow on the sky, no taste in the air, only a clean transformation from one set of rules to another, complete and without pain. Hold the idea as you would a delicate shell from an unfamiliar shore. Turn it once in the light to know its shape and set it back. Vacuum bubbles belong on a complete map. They show what fields can do when their landscapes hide deeper levels. They are not the likely end of our story. They simply remind us that the universe is written in fields as much as in particles, and that sometimes the largest changes happen without force, by choosing a lower energy in a quiet way. Let the room grow quiet and let your breath fall into an easy rhythm. We have walked through bright noons and long winters, through embers, horizons, and the thinnest afterlight. Now we turn home, carrying the far future as a gentle understanding rather than a weight. The universe moves by simple laws. Expansion widens distance. Entropy evens differences. Stars live on gradients and rest when those gradients fade. Black holes keep what falls, and with great patience, return it. If fields hide deeper resting places, their doors, if they exist at all, are set beyond worry. The likely ending is not a crash, it is an evening. After the last star forms, after the last merger, after the last horizon exhales its stored warmth, space holds a thin bath of low-energy light, and the lightest particles spread so evenly that hot and cold have no work to do. Engines fail not from damage, but from lack of contrast. Other pages exist in the atlas, and you have seen them. A pressure that grows too negative could unthread structure. A softened pressure could let gravity draw the cosmos inward, perhaps to a crunch, perhaps through a bounce. A deeper vacuum could retune the rules inside a racing bubble. Each path is possible in principle. None is demanded by the sky we measure. To keep these vistas soft, we rest them in calm images. Heat death is snowfall smoothing a field. A big rip is cloth pulled until threads separate. A crunch or a bounce is a breath turning inward that warms the room. A vacuum shift is a pond finding new stillness beneath clear ice. Images steady the mind while the numbers work. What remains constant is kindness to understanding. From the colour of distant light to the timing of quiet waves in space-time, the universe has written legible signs. Our hour lies in a bright middle, with generous gradients where life can shape small pockets of order by letting warmth flow into a wider cool. If the map changes, we will change with it. Better instruments may tighten the story or revise its footnotes. Either way, the timescales live far beyond anxious thought, and the tone remains gentle. Set this beside your breath. Inhale and think of gravity gathering stars. Exhale and think of expansion, giving nights their space. The end is not a threat, it is completion. A smoothing learned honestly over ages without number. Rest now, Voyager, a long day awaits.